Data-driven finite elements for geometry and material design. Data-driven FEM is a simulation algorithm that can handle runtime changes in geometry and material composition. Previous algorithms suffer from expensive pre-computation stages that rely on a priori knowledge of the object's geometry and material composition. Since this step is inside the design loop, the user cannot get rapid feedback on the changes made to the object. Our algorithm moves the time-consuming step outside of the design loop. We do this by constructing a custom metamaterial database that can be used to quickly coarsen an FEM mesh. We divide the object into a set of elements and coarsen these elements hierarchically. For now, we'll assume a single level of coarsening. Here, we have a block of 8 elements being coarsened into a single larger element. The top 4 elements are stiff, and the bottom 4 are soft. For illustration, we will work in 2D. Here, we have a 2x2 block of fine elements that we want to coarsen. We apply a deformation to the fine vertices and measure the resulting energy. We apply the corresponding deformation to the coarse vertices and place a sample point in the energy deformation space of the coarse element. We repeat this process many times to generate more deformation samples. Then, we fit a parameterized energy function to these samples. Additionally, our material model includes a term which accounts for anisotropy in our fine-level finite elements. To accelerate fitting, we search for the direction of anisotropy as a pre-processing step. We apply stretching forces of equal magnitude but different orientations to the sample and extract the stretching in the force direction at each quadrature point. We analyze this stretch in a 3D stretch space, performing PCA in order to extract the direction of anisotropy. The material IDs and the fitted parameters are stored in the database. The material IDs are the keys, and the fitted parameters are the values. We populate the database with other material combinations. In the online coarsening step, we perform a database query to assign the metamaterial to the coarsened elements. When the user changes the material, we use the material IDs as the key to the database to obtain the appropriate metamaterial parameters for the coarse element. After this process, the coarse mesh is ready for simulation. In this example, green is used to represent the results of high-resolution simulation and blue for those of our data-driven coarsening. Red and pink represent simple coarsening approaches which integrate the original material model and average the material properties inside each coarse element, respectively. We show results using both 1 level and 2 levels of coarsening.